Let me share my screen. Okay. So we're now on techniques of integration. And the first part here is on the natural logarithmic functions. The natural logarithmic functions, because we also have the common logarithmic function. That's the log to the base 10. This one is the log to the base e. So that is why it's written as ln, the natural logarithmic functions. Now, what is the integral that leads to this ln of u? So that integral is your u in the denominator and the derivative of your u in the numerator. So whatever function appears here in the denominator, it's a requirement that its derivative should be in the numerator. Then you can answer ln of whatever this u is. So in the first example, the first thing that you did here is make use of the primary rule of integration, the fundamentals, and that is whenever you have a constant, you write the constant before your integral sign. Whenever possible that you can have it factored from your expression, whether your expression is in the numerator or on the denominator. In this case, that constant here is 1/3. Okay, so you set it aside and you have the remaining expression, the integral of dx over x. This one is comparable to this. Your u is x, the du of this x is dx. So your answer is 1/3 ln of x plus c. Okay, let me this. Okay, now as you can see, you have here x squared minus 1. Now, if you intend to make x squared minus 1 as your du is 2x dx. Now, you already have an x in the numerator. So, what you're going to do, you place a 2 here, and you place 1/2 outside. This is 2 over 2, this one, which is just equal to 1. So, this is an expression equivalent to your du over u. This is your u, and its derivative is 2x dx. So your answer is 1/2 ln of u. And what is that u? That's x squared minus 1. You just completed the derivative in the numerator for your u in the denominator by multiplying it with a constant. And by the way, class, we can also multiply by expressions as long as it's equal to 1. So meaning we multiply, let's say for example, by x squared plus 1 in the numerator, then we should have an x squared plus 1 in the denominator. In that case, you cannot set that particular 1 over x squared plus 1 in that denominator aside. It should be interpreted together with your original integral. And that will complicate things. So it's only allowed when you're given already complex trigonometric expressions wherein even if you have that particular function in the denominator, it will still be possible for you to have the original function with that particular function together, but still it's still integrable. That's okay. But most of the time, class, we are only having less of a difficulty or less of a challenge if our manipulation here is just constant. So 2 over 2, 1/3 over 1/3, 1/4 over 1/4, something like that. Because constants anyway, you can set them aside in the process of integrating. Okay, so that's our sample number 2 for the ln. Now we go to number 3. Number 3, if you're going to look at it, is rational. However, the degree of the numerator is higher than the degree of the denominator. So this is second degree, this is first degree. I think your fundamentals in your senior high school mentioned, or if you can still recall it, that whenever the degree of your numerator in your rational expression is higher than that in the denominator, you will do first division. So you need to divide first. So you divide the numerator by the denominator. So this is what's done here. Okay? Distribute the x as a divisor, so you will have x remaining in the first term and you have 1 over x in the second. The first term can be evaluated using power rule. In this case, you'll have here on this particular expression is the application of the fundamentals we've learned. You evaluate this piece by piece. So you have here integral of x dx, and in here you have the integral of dx over x. If you integrate this, that would use power rule, x squared over 2, and this one is the ln of x. Of course, plus c because we're dealing with an indefinite integral. This is your answer. Now, number 4 has both the numerator and the denominator having the same degree. So if the degree of the numerator and the denominator is equal, you have to resort to long division. How do you go about doing long division? So you just divide x plus 1 by x minus 1. And you look at the first variables that you have here. So x divided by x is 1. So you multiply this entire expression by 1, so you have x minus 1. And what do you do in here? You add, or rather you subtract. So when you subtract, you cancel this, and this becomes added. So you have 2. What is this 2? This 2 is the remainder. And how do we write remainders? Is the value that we have here divided by our divisor, which is x minus 1. This thing you see here. Okay? Your answer, which is 1, plus the remainder, 2 divided by x minus 1. This one you can process right away because the first term is just the integral of dx. And the second term will be, I'm using the 2 basic rules in integration, set aside the constant, and you will have here dx over x minus 1. Now, if your u is x minus 1, the derivative of x minus 1 is dx. So it's in here. Then you can process the integral of this. The integral of the dx is x. And the integral of dx over x minus 1 is the ln of x minus 1. These 2 came from these 2 in here. The constant that is written before the integral. So far, can you follow? Do you follow? Are you still there, class? Okay. Let me clear the markings here. We go to example 5. It's a rational expression, a fraction. The degree of the numerator is less than the degree of the denominator. So there's no need for you to divide. You only do division when the degree of the numerator is higher to or equal than that of the denominator. If you set the u as x squared plus 6x plus 5, meaning this entire denominator here is the u, what is its derivative? It's 2x plus 6. Okay? 2x plus 6 dx. You can factor out the 2. That would be x plus 3 times 2. That this one is still equivalent to 2x plus 6. Now, since you only have x plus 3 here, you can introduce the 2 in here, and you place here 1/2 outside. So it's just like multiplying by 2 over 2. So now you have everything complete. So this is your u. The derivative is 2 times the quantity x plus 3 dx in the numerator. So it's an ln of u with 1/2 as the multiplier. So you have 1/2 ln of, what is the u in the first place? This one. So you just copy it, you just place it in here. So 1/2 ln of x squared plus 6x plus 5. Now let's try with a trigonometric expression. Tangent. If you recall the formulas that were shared to you regarding trigonometric functions, you don't have a direct trigonometric formula that can evaluate the integral of the tangent. So what you do, you write the tangent in its basic form, in its equivalent in the sine and cosine function. We know that sine over cosine is tangent. So sine x over cosine x. Now, you have a denominator, the cosine. If you set this as the u, what's the du? So the du is negative sine x dx. The only thing that you lack in the numerator is the negative sign here. And since you place a negative sign here, you place negative 1 outside. Equivalent to multiplying your original expression by negative 1 over negative 1. So you only need the negative here, the negative 1 in the numerator. So you still have another negative 1 in the denominator. So negative ln of u. And what is your u? That's the cosine of x plus c. Do you get it? Do you follow, class? Can you follow? Okay, let me stop sharing for a while. Okay, let me stop sharing for a while. I'll go to the Jamboard. Wait, class. Okay, I only have 2 students reacting, so I'm not sure if the others are still awake. So let's see. I'll write here integral expressions. I'll call your names. Let's see if you're there and if you can answer. Okay? Sige. That way, you'll be awake. So let's say the integral of let me check. Okay. Can I have somebody answer this one? Yeah, you dictate to me what should be the answer. We are on integrals yielding the natural logarithmic function. Let me check. Sige. Can I have Harvey Mabugat? Do you have your mic on, Harvey? Franz Mabugat? Harvey?
Hello? Hello,
Oh,
miss.
sige, sige. Okay.
Hello.
What should we do? I can hear you, Harvey. What should we do in here? Let's say given this integral, x minus 1 dx over x squared minus 2x. How do we write? or how do we determine its answer?
Mm,
What do we do?
you first.
What do we do?
No?
I hear you. I can hear you. So what do we do?
For me, miss, I think you have to expand it first.
What do we need to expand?
The whole, so the way I'm solving it right now, miss, is I made it into x minus 1 over x squared minus 2x plus 1, and then I expanded it by x over x squared minus 2x plus 1 minus 1 over x squared minus 2x plus 1. That's how I expanded mine, miss.
Okay, so this is
I,
in my understanding, this is the way you do it. You have x dx over x squared minus 2x
minus
plus
2x
1.
plus 1. Yes, miss.
And
And
then
then
you have
minus
minus dx.
1.
Oh, sorry.
Yes.
Yeah, dx over x squared minus 2x
2x plus 1.
1. Okay.
Yes, miss.
If that's the way you do it, Harvey, will it be
Mhm.
possible for you to integrate?
Um, I think pwede pa rin, miss.
How?
Mm,
Can this be integrated?
I I
No.
think not, miss.
Uh, can this be integrated?
I think, miss, if you apply these, if you apply, ano yung rule na yun? Forgot the rule.
Can we integrate this? What do you think, Harvey? Can this be integrated?
Feeling ko, miss, pwede, pero I'm not sure why.
This is not integrable.
Oh, okay.
But even if this is integrated, what will you do with this? It
Um,
will be a problem, right?
yes, miss.
Well, this one, so if I would go back to the intent I'm using here, you're right. So if it's just a guess, it's just a wild guess, then that guess of yours is correct because this can be written as dx over x minus 1 squared.
Yes.
If you'll have this expanded, it would be equivalent to this. And if your u is x minus 1, the du is dx, right? For this, if your u is x minus 1, the du is dx. Your n then, if you use power rule, will be negative 2. So that tells you that this part is integrable. So if you're going to integrate this just as an exercise, but of course you cannot use this method that you just suggested, you can have, if you use power rule for this one, you will have x minus 1 raised to negative 1 over negative 1, which is equivalent to negative 1 over x minus 1. However, you only have an answer for this one. This one is unanswered yet. So meaning you cannot use this procedure. But this one is integrable because you use the substitution. U is x minus 1. Du, what's the derivative of this? That's dx. Your n is negative 2. Negative 2 in the sense it's written in the denominator. So you use substitution here together with power rule. That way you can evaluate this given integral. But still, you cannot use this. Okay? You cannot use this entire suggestion because you only have one integral that was evaluated. This one remains not evaluated. Now, let me check what's in the inbox. Okay, so there was a suggestion here that you directly assign. So I'll use the suggestion of John Lapto. You first identify the UDU according to Marianne, and I think that's connected to what John is suggesting here. So let's go to the next slide and we'll have this evaluated. Oh, sorry. Now, I'll clear first what I have here. Okay, so if you clear what we have here, our original expression is you have x squared minus 2x plus 1, and you have here x minus 1 in the numerator, dx. Now, I'll go to the suggestion of John and Marianne. So you look for your u. So if you set your u to be x squared minus 2x plus 1, the du of this will be 2x minus 2, right? So if it's 2x minus 2, what do you lack in the numerator? To complete the derivative, you need the 2. 2x minus 2. You introduce the 2 here, you should have 1/2 outside. Then this could be evaluated using the ln that we just discussed. So it's 1/2 ln of x squared minus 2x plus 1. See, that's it. However, I say however, there's a much simpler process of doing this. Let me check if it's suggested here in the, okay, anyway, it's connected to what was previously suggested. Can anybody see a simplifying procedure that we can do here in the example? Ln of x minus 1. Jose Miguel, very good. Why is it ln of x minus 1? What did you do? Mr. Pido, why did you have the ln of x minus 1? How did you get it?
Yung factorable is ang 2x squared minus 2x plus 1.
Oh,
But yan.
again?
Pwede mas nga, 2x minus 1 over 2x minus, 1, yan factor ko lang pwede mas ang, 2x minus, 2 square minus 2x minus 1.
Again?
Then, factor ko lang mas para makancel mas ang x
What
minus.
did you factor? What did you factor?
2x square, inang x square minus 2x plus 1.
Very, very good. Very good. So this is what's supposed to be done. There's nothing wrong with this, okay? What Mr. Peter suggested is this. So you have x minus 1 dx. This is factorable. That's x minus 1 squared. What will you do? Of course, you take this out. You still have 1 remaining here. What's the resulting expression? The resulting expression is the integral of dx over x minus 1. So if your u is x minus 1, your du is dx. So then this must be the ln of u. And what is u? Because it's already u du. So ln of x minus 1 plus c. You see? If you have a keen eye and you're still very much connected to your algebra, it's simpler this way than this way. Now, somebody wrote in the chat box, ln of x minus 1 plus c. Precisely. Now, I'd like to ask you, is this answer different than this? Why is it that your answer here is 1/2 ln of x squared minus 2x plus 1? And this one is ln of x minus 1 plus c. Could it be that in, let's say, in a multiple choice quiz or exam, you will have two choices that are correct and you just have to choose on one of the choices? Are these two just acceptable? They are equal or what? What do you say? This one has a different answer. It may look like it's different. This one is different as well. Are they the same? Are they different but still both acceptable? Come on, CHE. You can do better than that. Are these two the same? Not the same but acceptable. What do you think? Danielle, Ong, are these two the same? Or they're not the same but they're still acceptable, Miss? Danielle, Ong. What do you
I think it's still acceptable, miss.
Are they the same? Equal?
Oh, wait, no, they're not, miss.
Okay, noted, noted. Okay. They are the same. You forgot your properties of the ln in the lesson you had just the previous semester. If we will simplify this one, whatever is written before the ln is an exponent of the argument of that ln. So this is actually ln of the square root of x squared minus 2x plus 1. And this is the ln of the square root of x minus 1 squared. What's the square root of anything that is squared? Isn't it like this? So they're just two the same expression. However, this one is written in the expanded form, whereas this one is written in the simplified form. As to question whether they are equal, they are equal. Okay, somebody wrote in the chat box, the other one was not simplified, Miss. Correct. The other one was not simplified, and this is the manner of simplifying it. That's correct, Pearl. When you simplify, you recall the previous learned principles and concepts, and that is when you have a constant written before your ln, that constant is actually the exponent of the argument of your ln. That will lead you to simplifying the argument itself. The square root of anything that is squared is the thing that is being squared. So this is just equivalent to this. Okay? Any question? Okay, so let's go back to where we are discussing because I don't want you to get sleepy with having to look on the examples here on the PowerPoint presentation. So we'll proceed with the next example. So here, still on the natural log. Okay, cotangent of x and the ln of the cosecant of x. Here we go. Cotangent of x over the ln of the cosecant of x. First thing that was done is to set the ln of the cosecant of x as the u, the entire thing, the entire function in the denominator. Now, what's the derivative of the ln? You've learned it last semester. The derivative of an ln u is du over u. Now, Let me annotate. So this is your ln of u. The derivative of this ln of u, its derivative is du over u. You differentiate this u and you divide it by itself. So when we differentiate the cosecant, this is the answer. The derivative of the cosecant is negative cosecant x cotangent of x dx. Then it was divided by the u itself. And what is it? It's the cosecant of x. So you have it here now, right? This negative cosecant and this cosecant will cancel each other when you process this one, giving you a du, a simplified du, which is negative cotangent of x dx. Do you follow? So this cotangent of x dx that you have here in the numerator only needs a negative 1 because the simplified du of your ln of cosecant x is this. So you place negative 1 or negative sign here and you place a negative sign outside your integral. So it's the negative of du over u because this is now your du and this is your u. And then the answer is negative ln of u. What is the u? The ln of the cosecant of x. So you write it. You write the answer as the negative ln of ln cosecant of x. Okay, we write here an absolute symbol or you write a parenthesis, that's okay. So the argument of the answer, which is a natural log, is another natural logarithmic function. Okay, this is the argument of this ln. Ln of ln cosecant x plus c. Do you get it? Can you follow so far? Any reaction? I'll give you a breather before we go to exponential function. I'll just finish the example 8. You have any questions so far? Okay, then we go to the last tier because we'll be discussing a different function after this, after our break. So you have 1 over the square root of 1 plus the square root of x. Whenever you see class expressions like this, it's okay if you do not know what to do at first. Okay, don't force yourself to really know right away what's supposed to be the u, what's supposed to be the du. It's okay to be normal that at first when you look at this, you don't know what to do. You're a normal student if you're like that. But the thing here, when you try, so I'd like to use the word try, when you try to check whether the given integral will yield an ln, is that you just set a u, a temporary u. It doesn't have to be that the initial u that you have selected should work for you right away. If it's your first u and you cannot complete the du of that, then forget about it. Choose another function that you have not chosen. Okay, so it could be in this case class that you may have chosen the 1 over square root of x as the initial u. When you determine its du, you will discover that this expression of 1 over 1 plus square root of x will be your problem because you can't do anything about it. So that's the time that you will change your option or you change to another option. It's better that I'll assign my u as 1 plus square root of x. Now, just do it one step at a time. If one u will not work, then choose another one. So in this case, if you choose 1 over square root of x as your u, what's the derivative of this? This will have a derivative of 0 because it's a constant. You treat this one as x raised to 1/2, so it will have a derivative of 1/2 x raised to negative 1/2. Because in differentiation, I think I need not explain this further. You subtract 1 from the exponent. So that would give this x that you have raised to 1/2 an exponent which is now negative 1/2. Because 1/2 minus 1 is negative 1/2. In that case, you have 1/2 x raised to negative 1/2 as this, right? And x raised to negative 1/2 is a 1 over square root of x. And this is your 1/2 here. Now, so this is your u. So the remaining expression, which is 1 over square root of x, only needs 1/2. So you place a 2 here, and you place 2 outside. So that's 2 over 2, which is still 1. So then you have a 2 du. This is your du. This is the entire du over u. Du over u. So you have 2 ln of u. And what is your ln? Or rather, what is your u? This is the u, the 1 plus square root of x. Another way of writing this is using your differential calculus last sem will be the ln of 1 plus the square root of x squared. Why? We just discussed it in the previous slide. This exponent of the argument of your ln can be written before it, just like the way it's written here. So whichever way you write it this way, or you write it this way, they're just two the same thing. So probably later on when it's multiple choice, you may keep on looking for this and you don't find it, but its equivalent is this one. So you have to still recall your previously learned concept in your EMA 101. Any question? Any question? Okay, so there aren't any question. I will clear my markings here. You'll have a 10-minute break. My time is 3:31. We will come back to the same, just don't go out of the Zoom link. Just come back 3:42 because it's 3:32 now. Okay, I'm just here. You can have your 10-minute break. So we now go to exponential functions. So we're done with natural logarithmic functions. We now go to natural exponential functions. And this is the formula. So exponential e raised to u du. You can copy the original given exponential function as long as, so the requirement is as long as the derivative of its argument, the argument which is the u, is complete. So it's eu du. So this should be interpreted that together with the exponential function, the derivative of its argument should be present or complete. So it should be eu du, and this should be your answer right away. So like for example, we start with a very simple exponential function here, e raised to 2x dx. Okay? So your u is 2x. The derivative of 2x is 2 dx. So what do we lack in here? You already have the dx, so you just need the 2. So you just multiply here by 2, and you place here 1/2, requiring you to multiply the entire integral by 2 over 2. So you have here now 1/2, as I have written here, eu du. In the sense that your exponential function is multiplied to the derivative of its argument. So 1/2 eu. And what is the u? That's your 2x. 1/2 e raised to 2x. Or you simply copy the original function. Because the integral of eu is eu itself as long as the derivative of its argument, the u, is complete. So you have this 1/2 e raised to 2x plus c. Can you follow with the first simple example? Okay, let me go down to the next. So we'll have this next one. Now this time, your EU is this. Now, this must be then your U. It's written here, x cubed minus 3x plus 1. What's the du of this? So you use power rule. 3x squared minus 3. You have a 3 here and a 3 here, so it could be factored out. So 3 times the quantity x squared minus 1. Okay? So you already have the x squared minus 1 here and the dx in here. So all you have to do is place the 3 and place 1/3 before the integral. So you have 1/3 EU du. And what's your EU? This entire thing. You just copy 1/3 and copy the original exponential function. E raised to x cubed minus 3x plus 1 plus c. So the integral of EU is EU itself. Okay? Just of course, multiply it with the correct constant when you try to complete its derivative. Any question? Okay, I think there's none. So we go to the next. Okay, this one is quite, these are those integrals that you will not know right away what to do, but it's okay to experiment. So you have here integral of e raised to x times the square root of 1 minus e raised to x dx. If you try to make your e raised to x as your EU, you will know right away that that's not the appropriate choice because you would still be left with the square root of 1 minus e raised to x. What will you do with it? So then, if you cannot make your EU as e raised to x, then maybe we can check if this one could be your u. Okay? We won't have here the expected EU du form, but rather what we can have is this expression that is under the radical sign could be now viewed as an expression which is raised to 1/2, meaning the entire 1 minus e raised to x. If your n is 1/2, I'd like to write this as in that form, that way you will follow. If you write it as 1 minus e raised to x raised to 1/2, that one, then you can check whether power rule will work for this. So this is not really, as again, I will emphasize, this is not an integral that will yield an EU, but rather an integral which has an exponential function that will use the power rule. Okay? Just a moment, class. Okay, it's done. Now, you have here u as 1 minus e raised to x. This must then be your n, if we'll have power rule. The du of this u is, of course, this one is a constant. It will have a derivative of 0. The derivative of EU is EU du. Whatever is the u here, in this case, it's x, so the derivative of that is dx. So the derivative of negative e raised to x is negative e raised to x dx. Okay, so this is the derivative. You could see that you already have here the e raised to x and the dx. You only need to affix the negative sign. So you place the negative sign here and you place a negative sign outside, requiring you to multiply by -1 over -1. So in that sense now, class, it could be written as the negative of the integral of negative e raised to x square root of 1 minus e raised to x dx, where you can use power rule. Where will you use power rule? In here. So if you use power rule, I'd like to simplify this further by writing it in this form so you can easily follow. So negative integral of, I'll write 1 minus e raised to x raised to 1/2. Okay, for this one, then I will multiply it by negative e raised to x dx. So you will see that this is your u raised to n and this is your du. So if this is your u raised to n, if you use power rule, your answer will be, so you have the negative here, negative u raised to 3/2 because you need to add 1 here. and over 3/2 plus c. So in that sense, you will have negative. These 3/2 here, when written the other way around, not in the denominator, will be 2/3 times the quantity. What's the u? This one. 1 minus e raised to x raised to 3/2 plus c. So this is not an integral that yielded an e raised to u expression, but it's an integral that contains a natural exponential function where you apply the derivative of 2 power rule. So power formula, gid ang gingamit dire. But you made use of the derivative of the exponential function to make it happen. So this is the answer. Do you follow? Do you have any questions? Okay, so I'm sure everybody follows because nobody asked question. Now next, so we'll have the fourth. Now this time we'll have an e tangent of x, second of squared x dx, second squared x rather dx. Now this time we can check whether it's possible that we will have our EU as the E tangent x, meaning the U is the tangent of x, the DU is the second square root of x dx. So here it is. So since the derivative of the U is complete, the answer is E tangent x. So you just EU du is EU plus C. Now for this one, this is not again, an example which will yield an exponential function, but it contains the natural exponential function. If you will make this as your function to be integrated, the cosine of e raised to negative x, this will be your cosine of u. Your u being the e raised to minus x. What's the derivative of e raised to minus x? It's negative e raised to minus x dx. Right? Now, you have it here already, the e raised to minus x dx. What you lack is the negative sign. So you place the negative sign here and you place negative outside. This will be integrated, class, not as a function that will be exponential in answer, but rather as a trigonometric expression which contains a natural exponential function. What do I mean by that? You will integrate it using the formula for the integral of the cosine. You only use the concept of the derivative of the exponential function in here. And to complete the derivative of the u in this cosine function, which is exponential in nature. So what's the derivative of the cosine? It's positive sign. But since you have negative here, so you could see here, negative sign of e raised to minus x. Because our primary function that was integrated is not exponential, but rather trigonometric in nature. Do you follow? Let's say, for example, you don't really know what to do. You look at it. So I will try to set my EU as e raised to negative x. You just try. Now, if you set it that way, the derivative of your negative x here in your EU is negative dx. So, okay, I have the dx here, and I can place the negative sign. But the big problem, class, is you haven't done anything on this function. So it tells you that your exponential function here is not the primary function that has to be integrated. It's just the function that could be used in integrating probably the other one. And that the other one that I'm referring to is the cosine. The cosine of e raised to minus x. So it's just like that in integral, that whenever you assign a function to be the main function integrated, and it seems like there are still other functions that cannot be dealt with, you can't do anything about them, then the original function that you have chosen to evaluate is not the original function, or is not the main function, but rather it's just a function that's written there to probably provide the derivative of the others that goes with it. So just like in the case of this example, number 5. I hope I make sense. Do you have any question here? There's none? Okay, so I'll close now. We'll go to the next. Okay, so that one is natural exponential. Natural, meaning exponential function siya. What about if it's the general exponential function? Clear my markings? When we speak of a general exponential function class, the base is a real number. This could be 2, this could be 100, this could be real number, 1/2, 1/4, or -5, something like that. But in this case, we cannot have a negative because we don't have an ln of a negative number. So we'll just have this a as any positive real number. So you have a raised to u du. Just like the way we have it in natural exponential function, you will also have an answer which is au. If this is e raised to u, your answer here is e raised to u plus c. Here now you have au and you have also au here. But you add the reciprocal of the ln of its base. The base which is a real number, a positive real number. So ln of a. Just like the way you view the u here in the natural exponential function as to be the expression that has to have a complete derivative here in the du, that should be the same with this one here. You will have only this answer for an a raised to u du if and only if the derivative of the argument of your a here is complete. So you have to make sure that your au is multiplied to the derivative of its argument, the u. Then you can also have the au here, just divide it by the ln of the a. Okay? I hope you can follow too. It's the same as the eu, only that this one is a real positive quantity for the base. Okay, ln of a. Now, I will clear my markers here on top so it would be clearer when I explain the example here. So this 5a raised to x squared is your a raised to u. Okay? Then your u then must be your x squared. The du is 2x dx. Your a is 5. So the a is 5. You can see here. A is 5. You see that? Now, if you need a du, which is 2x dx, you already have an x here and a dx here. So what you need is just the 2 in here and the 1/2 before the integral. And that's it. You have 1/2 integral of au du, or 1/2 ln of a, which is 5. Then copy the au. What is your au? 5x squared. So you have 1/2 ln of 5, 5 raised to x squared plus c. And that's it. You just make sure that the derivative of the argument of your a is complete. So we just made it complete by dividing by multiplying rather by 2 and dividing before the integral, dividing your original integral by 1/2. Do you follow? That's your natural exponential function. Okay, I will proceed. Any question here? Okay, good. So we go to this one. Cannot change slide. Okay, number 2. 3 raised to cosine of x sine x dx. This is your au. Your a is 3. Your u is cosine of x. The du of that is negative sine x dx. You already have the sine x dx here, so you just need the negative sign outside. So it's written like this: negative integral of 3 cosine x times negative sine x dx. So what's the answer of this? Negative of 1 over ln of a, which is 3 au, meaning this original expression, 3 cosine of x plus c. Do you get it? Questions? Okay, so clear. We go to the next. This is, I think, my second to the last for the day. Now, 3 ln of x squared over 3 dx. 3 raised to ln of x squared dx over x. If this one is your a raised to u, your u must be ln of x squared. The derivative of ln, we discussed it a while ago, is du over u. The u of your ln is this, x squared. Don't confuse this u here to the u in here of your a raised to u, because your a raised to u here has the u as the ln of x squared. But when we speak of the ln of x squared only, its u is x squared. So it's du, the d of x squared is 2x dx over u, because the derivative right here, the derivative of ln of u is du over u. So this is your du, and you divide it by the u, which is x squared. In the process, you can cancel this x here, and you still are left with 1x here. So it's 2 dx over x, right? Now, this dx over x, this is already the dx over x here. So you only need the 2. So you place the 2 here, place the 2 in here, and place 1/2 before the integral. So in the process, you have 1/2 now. If I will rewrite this, so it would be clear, 1/2 integral of 3 ln of x squared. The derivative, sorry, should not be 3 ln of x squared, but rather 3 raised to ln of x squared. 3 raised to ln of x squared. Its derivative is this one, the 2 dx over x. So you place here 2 dx over x. I just transferred it here so you would see. This is your au and this is your du. So what's the answer for this? You have to, of course, incorporate the 1/2. So 1/2 au. So your au is 3 raised to the ln of x squared over ln of, what's the a? 3. So this is your answer. You have 1/2 3 raised to ln of x squared over ln of 3. Or you can group this together the way it's written here. Do you follow? Okay. Then we have this one. The last example. Do you have any question here? Okay, the last example is this one. This. Okay. You may look at it, there's just so many things written here. How am I going to make my way through in here? When I was a student, I would normally look for the most complicated function or expression in my given integral and consider that as my main function. The rest that I see there, I temporarily think of it as the derivative of my main expression. So that's my hint to you. Whenever you see a complicated expression, choose the complicated expression, the most complicated of the functions you see in your integral as your main function. The rest, temporarily, think of them as your derivative. So if you'll have that notion here, then this 6 xe raised to x must be your a raised to u. Your u is xe raised to x. If you're going to use differentiation here, this is not the usual differentiation in which you have a single answer. Why? Because you have to use product rule here. What's product rule of differentiation? The first term, I'll place it in here. So you would see that that's the answer. The first term times the derivative of the second plus the second term times the derivative of the first. So it's xe raised to x plus e raised to x, as you could see here. And you could see that this e raised to x is factorable. So you have e raised to x times the quantity x plus 1. So you see, this e raised to x times the quantity x plus 1 dx in here, which I temporarily considered as derivative of my most complicated expression, really is the derivative. So it does not have anything to do with the main function except that it's meant to represent the derivative of the u of my main function. Now, so this is the derivative and your a here is equal to 6, the base. That's right. So your answer now will simply be au over ln of a. As per the formula, this is your au and this is your 1 over ln of a. Do you follow so far? So this afternoon, how many new things have you learned? You have learned the natural logarithmic function. You have learned the exponential function. And you have learned the general exponential function. So these functions are evaluated in the integrals that were shown to you or is part of the expression that needs to be evaluated. You add these learnings that you have to the original formulas that were discussed last meeting, the trigonometric function, and the process of substitution. Now, I will stop sharing here. Do you have any questions? You have any questions, class?